In this video, we're going to continue talking about our kinetics of a particle as we've talked about with force is mass times acceleration, as we've talked about with work and energy. Now we're going to talk about the concepts of impulse and momentum and where those things kind of come from. So if we think about like our force is mass times acceleration, Newton's second law, really kind of basis of pretty much everything that we're doing in this class, everything related to our kinetics of a particle, is our F equals ma. So if I go ahead and convert that acceleration into being in terms of velocity and time, dv dt, if I move that t over, f dt is going to be m dv, and if I integrate each of those sides, what I'm going to get is the integral of all of the forces, so the summation of all of the forces that could be working in a system is from t1 to t2, that integral of the forces dt equals my integral of mass dv from v1 to v2. M dv, where v is my velocity. And so what I get from this integration is what we call the principle of impulse and momentum, where I'm getting the integral, the summation for all of those forces, integral from t1 to t2 of the force in terms of time, dt, equals mass times velocity 2 minus mass times velocity initial. And this is what we call our principle of impulse and momentum, where we can see we kind of get these terms that we remember from physics, where we have this mv as our momentum here on the right side of our equation, mv, and I'll use the letter L to represent our momentum. You may use another letter. This is the one that our book uses, but this is our linear momentum. L equals m times v, and on the other side of our equation, this integral of f dt, I'm going to call this I, for impulse. So our principle of impulse and momentum is literally just our impulse, our change in impulse there equals our change in momentum. Or you may see it rewritten like our initial momentum plus the impulse equals our final momentum of whatever movement of this particle. So this can be a really handy setup, a really handy derived equation that we, don't have to derive ourselves. We went through the derivation, but this derived equation can be really useful for when we're solving problems that involve force, time, and velocity, right? We can cut out the middleman of having to solve the acceleration. It's really, really good for finding a final velocity after a specified time. That's really like what it's most commonly going to be used for, is finding final velocities after a specified time when you know the force and you know an initial velocity. One thing to bear in mind with these is that these are vectors, which I should put in here. My force is a vector, and those velocities are also vectors. So we'll need to bear in mind that when we're doing these, we're going to have to treat them as vectors, or we can treat them as scalars by breaking them up into their components. So typically with these, we're going to be working in the XYZ system. So it may be easiest to work with these where we have the summation of all of our forces integrated over time for all of our forces in the X direction. dt plus our initial momentum times our velocity in the X direction is going to be our final velocity in the X direction, right? So breaking them up into their X and Y components, we can do it for Y as well. Sum of all the Y forces dt plus the mass times the Y velocity, 1 equals mass times final Y velocity. And you can do it for Z as well. So a lot of times it's easier to kind of break it up and do a scalar analysis. Just as we do in statics when we do, sum of x forces, sum of y forces, we can break it up the same way here. Makes it a little bit easier to solve these problems. Now, solving these problems is going to look a lot like how we solved our problems with the principle of work and energy, which is where we're going to establish a coordinate system. And again, it's usually going to be x, y, z for this principle of impulse and momentum. We're pretty much only dealing with linear impulse, linear momentum. That's what these equations are for. But we'll still go ahead and establish a coordinate system. For example, we may want to rotate. Maybe our xy isn't our traditional xy. Maybe it's rotated, something like that. So we'll establish our coordinate system. We're going to draw our free body diagram, of course, to help us assess what forces are going which directions, which forces we need to account for in our free body diagram. And then we can also draw, if you find it helpful, we can draw what we call impulse and momentum diagrams. So for our impulse and momentum diagrams, impulse and momentum diagrams, this can be helpful to establish like directions of velocity and directions of the overall forces. So what that might look like is we have, we've got a particle, and let's say it initially has a momentum of m times v1 and is going in this upper right direction. So this would be initial momentum, which would be this term right here, right? Either one of these terms. We have our, actually I'll keep that, our initial, circle it just on my x's though. Initial momentum plus our impulse, so that's the way the sum of the forces are acting on it. So maybe the impulse is acting like this, and this is our summation of f dt. Right, our first term, this is our impulse. And that's going to equal our final momentum, right? So how the velocity changed after being affected by those forces. mv2, that's final momentum. And that's the final term in our equation there. So this is the impulse and momentum diagram. Could be helpful to you to assess all of those directions if we've got multiple, especially if we've got multiple going on in the x, y, and z directions. It can be very helpful to divvy those up. Then we're going to apply our equation, right? Apply our principle of impulse and momentum. And 5 would be using any other strategies that we've learned so far to solve for bits and pieces that we may not be able to solve for just with our principle of impulse and momentum. So this may be any additional kinematics we need. This could also be our F equals ma, right? Our equation of motion. Maybe we need to apply this. Maybe we need to do some statics on our free body diagram to solve for, say, maybe you have a weight and a normal force, maybe you have multiple forces, you need to solve for a normal force to get some kind of friction, something like that. Maybe even the principle of work and energy that we had been using, conservation of energy, any of these work and energy equations, any of those relationships that may help us find what we're missing in this principle of impulse and momentum. So with this in mind, we'll go ahead and take a look at a couple of examples. In this example, we've got a 100-kilogram crate that's shown rests on a smooth horizontal surface. So of course, a smooth surface means that we're not going to have to account for friction. If a towing force of 200 newtons acting at 45 degrees is applied for 10 seconds, determine the final velocity of the crate and the normal force which the surface exerts on the crate during this time. So before I do anything else, I'm going to draw my free body diagram. So I've got my crate here, and I know that I have that 200 Newton force on it. FBD. Here's my free body diagram. My crate has a weight, right? It tells us that it has a mass of 100 kilograms. So my crate is going to have a weight, and that's going to be the 100 kilograms times 9.81 since we're working in SI units. And then on that surface, again, no friction, but there is a normal force from the surface. So let's see if there's any other, and then of course this 200 Newton force that we've drawn is acting at a 45-degree angle. And now we can see, make sure there's not anything else useful in here. So we've got a 100 kilogram crate, smooth surface, 200 Newton towing force. Our time applied is 10 seconds. And we want to find final velocity, so that's our V2, and we want to find the normal force. Now, of course, our normal force we could find just using our F equals ma, just using our statics. Since there is no acceleration in our y direction here, we could solve it that way, but we're going to go ahead and solve it using this impulse and momentum just to kind of see how it works. So first things first, let's write out our equation. Right now that we know what we're looking for, we've got our free body diagram. Let's try applying our principle of impulse and momentum. So that's going to be mv1 plus summation of all of the forces. And in this case, I'm going to do our x direction since that's the direction of our motion. So before, let me just change this, our v1 x direction, summation of our forces in our x direction from t1 to t2 dt equals mass times velocity 2 in our x direction, right? No movement in our y direction. We're only going to need to look at the x scalar form of this equation for this particular problem. So now that I've got this, I can kind of start plugging things in and see what I need. So my m times v1, my v1, it says our 100 kilogram crate shown rests, right? So we're going to assume that our box is starting from rest and then this towing force is applied. So we're going to start from rest, which means our initial velocity is going to be 0. No initial velocity, no initial momentum. And then we'll come look at our impulse terms. So in this case, we only have one force that is acting in our x direction, and that is the x component of this 200 Newton force. 200 cosine 45. It's our only thing that's causing any motion. So that's going to give us 200 cosine 45 for our force component, x component of our force, dt. Since this force is consistent, it's not changing with time, I don't actually have to do my integration. I can just say my force times t. You know, kind of like we did with work, where you could do your work is the integral of our, my mind is drawing a blank, our integral of our force dr. Just like our work is our force dr, that sometimes we treat as force times just the overall change in position, this works the same way, right? Just that integral of a constant is going to give you the constant times the time there. In this case, this is our fx. Our dt is from 0 to 10 seconds. And that's going to equal our mass times V2, mass of 100 kilograms times our V2. And from here, it's pretty straightforward to solve. We can just plop this into a calculator and get that our final velocity, since our velocity is only in the x direction, final velocity after 10 seconds is 14.1 meters per second. So pretty straightforward. It functions a lot like our principle of work and energy, where we had the initial kinetic energy plus the work, summation of all of the works from all of the forces, equals our final kinetic energy. This works the exact same way, where now we're taking initial momentum plus the sum of the impulses from all of our forces equals our final momentum. It's going to work the same way. The math works out just the same way. So let's do our normal force. This is the last piece that we need. And again, while we can solve it other ways, we can solve it with pretty much any of the multiple principles that we've talked about so far. You can solve it with statics. You can solve it pretty straightforward. We're going to just solve it, showing that you can solve it with this impulse, principle of impulse and momentum. So our mv1, now in this case, not 1x, we're going to look at our y components. Okay, so we already did our summation of our x components. Let's look at our y components. Plus summation integral t1 to t2 fy dt, since that normal force is in our y direction, equals mv2y. Now, of course, we know this crate is only moving in our x direction. There's no movement, there's no velocity in our y direction at any point from that applied force, which means both of our momentum terms are going to go to 0. There is no velocity in the y direction ever in this system as it's presented. So that means we can just use our impulse term to find what that normal force is. So looking at our free body diagram, we're going to need to account for all three forces with their y components. So I'll start with my normal force. This normal force times the time, 10 seconds, going upwards. My other upwards force is the 200 sine 45 plus 200 sine 45 times its time minus the weight, which is 100 times 9.81 times the time of 10 seconds. And that all equals 0. Right, we got rid of those two momentum terms. Momentum is just 0, so this all equals 0. Really, all these 10s cancel out, and you end up with the exact same thing, the exact same equation that you would have gotten if you just did it via statics, where you just did sum of all the forces equals 0, since all these 10s cancel out. So from this, we get 840 newtons with our little bit of algebra there. So again, ends up working out the same way. You can try it for yourself. If you try doing summation of forces in your y direction, try doing it by statics, you'll get the same thing either way. So just know there are usually multiple correct ways to get to an answer. You can do this principle of impulse and momentum, you can do your principle of work energy, you can do your equations of motion, sometimes your statics, F equals ma, those things. Lots of tools in your tool belt now, lots of ways you can get to correct answers, and we're just going to keep building onto this one. Right, again, this one is really, really useful for final velocities, but you may find it useful for other problems too. Let's go ahead and take a look at another example. All Alright, so in this example we have a 200 kilogram crate that rests on the ground for which the coefficient of static and kinetic friction are, coefficient of static friction is 0.5, coefficient of kinetic friction is 0.4. The winch, which is this little blue fan looking guy, he's a motor, he's a winch, delivers a horizontal towing force T to cable A, which is represented by T equals 400 times T to the 1/2. So uppercase T here is tension in the rope, and lowercase t is time. So T, uppercase T equals 400 times lowercase t to the 1/2. Determine the speed of the crate when T equals 4 seconds. So lowercase t, time. When time is 4 seconds, we want to know the speed of the crate. We want to know V2. And originally we're given that there is 0 tension in the cable. So there is no tension in the cable, and then when this starts, the cable starts tightening and tightening until that winch starts to actually overcome static friction from the ground. There's full tension in our, or I guess I should say increasing tension in our orange rope there. And now the box starts to move to the right. It starts to move towards the winch. So we want to know V2, given initially that it's sitting at rest, and with an initial tension of 0. No tension in the cable, initially sitting at rest, then the winch comes on, and we want to know 4 seconds after that winch comes on what the speed is. So first things first, let's do our free body diagram. And so my free body diagram for this crate, draw my little crate, and then I'll draw my forces in. So for my crate itself, I'm going to have the normal force from the crate on the floor. My crate, of course, has a weight from that 200 gram mass, or 200 kilogram mass that it has. And I know I also have a frictional force. I've got a frictional force, one for static that I have to overcome before that movement, and then I've got a frictional force after that movement has started, that kinetic friction. And then I have this pulley system here, right? I've got the force from this pulley. And what I'm actually going to do is I'm actually going to include this pulley in the free body diagram. I'm not going to make it its own separate free body diagram. And the reason for that is because my pulley and my box are moving at the same acceleration. They're not going at 2 different accelerations. They're moving together towards the right. So I'm going to treat it just as if it's part of the box itself. And from that, it has the tension coming off of it. So again, that rope goes over the top and under the bottom. It connects to a post at the bottom and then is being winched up through the top rope there at A. But both of those ropes, right, going over that pulley there, are going to have the same tension in them. Both of those ropes have a tension of T at any given time, that uppercase T, 400 times T to the 1/2. So this is going to be my full free body diagram. Again, crate and pulley included as one, since they have the exact same acceleration. Now that I know this, I've got to think of what's happening, what's actually happening in this system. So again, I have no tension in the rope at first. I have to overcome my static friction before the crate ever starts moving. So really what's happening is I've got kind of 2 time intervals that are happening, which is initially my box is at rest. Right, and as the tension is growing in those ropes, the static friction is fighting back. Right, so there's a time period where the winch has turned on, but the crate is still not moving. And then once it finally overcomes that static friction, then I have my kinetic friction where the box is actually moving to the right. It actually starts accelerating after that point. So I've got really 2 time intervals that I need to account for here. I can't just skip forward and say that it like is immediately moving as we have done in problems in the past, right? So most problems we say that, okay, this force is enough that it just immediately starts moving, overcomes kinetic friction, or overcomes the static friction immediately, so we don't even account for that time interval. But this time interval is going to be pretty significant since we're only looking at this time period of 4 seconds. So we're going to look at first what that time period is of static friction before we get into the kinetics where we can find that final velocity. So for our first part here, I'm going to say we need to find the time and force before it starts sliding. So before sliding, we can just treat this like a statics problem. Right? We can just do our summation of forces in our y direction is 0, which obviously we know that was going to be the case either way. And summation of our x forces is also going to equal 0 because during this time interval, the crate is not moving. It is in static equilibrium. It's not accelerating until it overcomes the static friction. So during the static friction, only statics is going to apply. I'm going to say my sum of y forces. I have my normal force from my free body diagram, that normal force minus the weight. Weight, of course, is mass times gravity. 200 times 9.81 equals 0, which is going to give me a normal force of 1962 newtons. And if I do my summation of all of my x components there, I'm going to have 2t minus my friction equals 0. And really I want to start plugging some things in there. So I know 2t, that uppercase T is 400 t to the 1/2 minus my frictional force, which is going to be my static coefficient of friction, 0.5, times the normal force. 1962 equals 0. And so my only unknown in here is the time. So I can solve for that time and figure out how long it takes before this box starts sliding. And in this case, when I punch it into my calculator, I'm getting right around 1.5 seconds. So that's a pretty big chunk of time. It's almost half of our time interval, you know, it's like a third of our time interval where the crate is not moving at all. So we have to account for that when we're doing our principle of impulse and momentum. We have to account for that not moving time interval. And then so right after that 1.5 seconds, like immediately after, it flips over and now this thing is starting to accelerate. So this is where we can switch over to our kinetic friction and solve using our impulse and momentum. Keep that right there. Let's write out, now that we're after sliding, or so we started sliding. Say that. So we start sliding at t is 1.5 seconds. So under this scenario, we're going to have m times v, and again, everything is moving in the x direction, no movement in the y direction, or no velocities, no acceleration in our y direction. So this is going to be our x, 1, plus the integral from t1 to t2 of all of our forces dt equals m dx2. So looking at this, let's start plugging some things in here. We're going to have our mass times our initial velocity. Now again, right when it clicks over, right when we start movement, really at the very beginning of the movement, our velocity is still 0. We still have 0 momentum. It is so infinitesimally small at the millisecond that we start that our initial momentum term is going to go to 0. So we're going to have 0 plus, now we're going to take a look at our forces. So our 2 tension forces and our frictional force are all contributing. Right? They're all contributing to our impulse. These are all the external forces on the system in our x direction. So we have 2t, and that t again is changing. Right? This t is changing over our time interval. So what we're going to have is the integral from our initial time, which is now 1.5 seconds and not 0 seconds, to the final 4 seconds is going to be 2 times the tension, 400 times little t to the 1/2 dt. So that accounts for the impulse of the 2 tensions. I also want the impulse from our frictional force. And now our frictional force is actually a constant, right? It's just going to be mu times n. N is not changing, mu is not changing, which means we can do minus, since it's in our opposite direction, minus mu, which is 0.4, now that we're going in that kinetic one, not our static one, 0.4 times 1962 times the time interval. Very important that we know it's the change in time here, or minus 1.5. Right, so it's not just 4 for the entire time interval, it's only for this time interval that the movement is happening. And this whole thing, those are all of our forces are accounted for in our impulse. This whole thing is going to be equal to our mass, which was 200, times final velocity. So now from here, we can go ahead and plug things in and solve for what this v2 value is. So I can take this integral, so I get 800 t to the 3/2 over 3/2 from 1.5 to 4 minus this value. When I type it in my calculator, I just get 1962 for the second term, equals 200 v squared. So now that I plug in my upper and lower bounds into t, pop this in a calculator, divide by 200, I get v2, that final velocity, is 6.62 meters per second. Right, so there's a lot of different skills that we've combined here, a lot of different analyses that we've done, bearing in mind that we had the static and then the kinetic friction, making it into 2 different time intervals for us. So these are just some of the things that we'll have to keep in mind for these dynamics problems, which I know is really hard. I know it's really hard to, every single time you're given a problem, you have to really truly analyze what's going on. There's not really like a good general rule of, always do this exact process this way every single time. It's really taking a look at the problem, seeing what the motion is in the problem, how it's actually working, and then deciding how you want to approach it. So these are all just more tools in the tool belt to help you solve problems. That's why we keep adding on all these equations and having you learn them and work through these problems, because it just gives you more ways to solve these problems, since every problem that you encounter in the real world is kind of unique in some way. So let's take a look at an example that's a little more real world. For this next example, we'll go ahead and take a look at something that could be a job you have if you go into automotive manufacturing and we want to do performance safety crash tests, for example. So we're going to look at a crash test of a BMW i4, and we'll kind of just watch this video and see what that looks like.
The test will commence in 4 seconds. 3, 2, 1. The vehicle is underway.
So as engineers, safety is often a top concern for us, and so it can be really important for us to calculate things like how much force is a vehicle going to experience when it goes into a crash, right? So that's what we're going to calculate in our example problem here. So we have what we just saw, the BMW i4 undergoing safety crash testing. The model tested weighs 4,700 pounds and is traveling at 40 miles per hour when it crashes into the wall. The impact occurs in 0.5 seconds. Determine the impulsive force acting on the car, assuming no brakes are applied. Right, so it looked like no brakes. They had just crash test dummies in the car, nothing to apply the brakes. And they did say at the beginning of the video that it was traveling at 40 miles an hour. So we're going to go ahead and find what that impulsive force was on the car to bring it to a stop. So first things first, let's look at our free body diagram. I've got kind of like a very rough sketch of what happened, but there's nothing better for us than a free body diagram, really putting all of those forces out there, showing us exactly what's going on. So obviously the car's on the ground, it's going to have its own weight of 4,700 pounds. That's 4,700 pounds. It's got the normal force of the road acting on it. And then it also experiences the force from the wall, right? That force is really what's stopping it. And we have that our initial velocity is 40 miles per hour, and our final velocity, of course, is going to be it coming to a rest, right? So that impact occurs in half a second, and after that half a second, it's now at rest. In the time interval 0.5 seconds, we want to find what F is. I've got my free body diagram. I wrote out everything I know. Now I'm going to apply this principle of work, principle of impulse and momentum. That's the one we're doing. Sorry, I'm a couple weeks behind mentally, I guess. So our principle of impulse and momentum, again, everything is in the x direction. No impact is happening in the y. So it's going to be our m times velocity in our x direction. 1 is the summation of all of our forces in the x direction over the time interval equals our final mass times velocity. So one thing that we probably want to do before we start plugging things in is noticing what our units are. Right, so our weight is 4,700 pounds. That's pretty standard. But these velocities are given to us in miles per hour, which is, great for reading your odometer in your car, like great for getting your speed from your car, but not super great for having mixed units, right? Our time is in seconds. So it doesn't really make sense to have something in miles per hour if our time interval is in seconds and not hours. So let's convert that real fast. 40 miles in 1 hour. If we convert that from 1 hour to seconds, is 3,600 seconds. And then from miles to feet, 1 mile, and I'm doing it this way so I can kind of like cancel my units as I go along. 1 mile is 5280 feet. And it's okay if you don't know that offhand. You can Google conversions. You could Google conversion from mile per hour to foot per second. That's fine too. This is going to get me that my initial velocity is 58.67 feet per second. So now all of my units are consistent. Start plugging stuff in here. My initial mass is going to be, again, for our US units, you have to divide that weight in pounds by gravity to find what the mass is. 4,700 over 32.2 gives us our mass in slugs. And then our initial velocity, we just said, was 58.67. But notice this velocity is going in the opposite direction of our force. Right? Velocity is going to the left while force is going to the right. So one of these is going to have to be negative. They're going in different directions. So you can make either your force in the negative or your velocity in the negative. Here I'll pop in negative on my velocity, and I'll say that this way is my positive convention for x. Going to the right is going to be my positive convention. So 4,700 over 32.2 times negative 58.67. Plus my forces. Now I'm going to assume that the force is consistent over this time interval, this very small time interval. I'm going to just find like an average force here. So my force times the time. Force times 0.5 equals my mass times my final velocity. So 4,700 over 32.2. And then final velocity is, it comes to rest, right, after that crash. So really our whole term on the right side goes to 0. And what we end up with is 8563.15 equals our 0.5 times F. So that force that the car is experiencing from that collision is 17,126 pounds. That much force that the car has to absorb, and if it doesn't, some of that gets transferred onto the person inside. And you can see that a little bit with the crash test dummies, that they experience some of the force as well. Usually not the entire 17,000 pounds of force, but some of the force does get transferred to the people inside. That's why we really like our vehicles to crumple and take on a lot of that force before it reaches the people inside the car. That's why we do these crash tests to see kind of how the car fails, where the car fails, how much force, how much, like what is happening to the car when inevitably it, someone somewhere will crash the car and it will fail. We need to know how that failure occurs and what's happening to the people and how can we keep them as safe as possible. All right, so I've got one last one for you to work through, and then we'll talk through it together. So if you want to go ahead and pause the video, read through it, work it out, and then compare to the answer that I get and see if you're understanding the concepts we're doing here today. So this says that a 50-pound crate is acted upon by a force having a variable magnitude of 20 times t being time, 20 times t pounds. Determine the crate's velocity when t equals 2 seconds if the initial velocity of the crate is 3 feet per second down the plane, and we're given a coefficient of friction of 0.3. So go ahead and pause the video, attempt this for yourself, and then we'll work through it together. All right, so let's go ahead and take a look at this. First thing we're going to do, of course, always, is our free body diagram. So that we can look at this and understand what forces are acting on it, what kind of motion it's going through, and it's on this plane. So I have a 50-pound crate. So it has a weight of 50 pounds that is being towed by force P here. P is 20 T-pounds. So P is a variable force. It's changing over time. Determine the crate's velocity when T equals 2 seconds. So we know T is 2. We know the initial velocity, V1, is 3 feet per second. We know mu is 0.3, just from picking out these important things. And then I did not finish my free body diagram. How bad of me. I need to finish that. Of course, the crate has a normal force from that slope that it's on. And then finally, it has friction. We know that from our coefficient of friction. We know that because it says, or it doesn't say that it's a smooth surface. So we're going to assume that we've got friction up the plane since it's moving down the plane. Now I have a complete full body diagram. I have written everything that they've given me in this problem. And I'm going to go ahead and attempt to solve using that principle of impulse and momentum. So my principle of impulse and momentum again is going to be m times v. And remember, I've got to split this up into its scalar components, right? I've got to pick an x and a y direction. But this is moving like down the slope, right? It's moving in like a traditional, if I keep my x and y direction as x and y, then it's moving in both x and y direction. But if I want to make this problem a lot simpler for myself, what I can do is I can skew this, right? I can rotate my traditional xy and I can say, okay, my x value is going to be down the plane and my y value is going to be perpendicular to the plane. And I'm going to work with my values like this. So here, now I'm doing my new rotated x direction. Since that is the direction of my motion, that's the direction, that's the only direction we have velocity in, is up and down the slope. So m dx1 plus summation of all my forces dt, and all my forces times time, equals mass times my final velocity. And that's what we're trying to find, right? We're trying to find what that final velocity is after 2 seconds. So I'm going to start plugging things in and see how far I can get with this. So my mass, of course, we were given a weight of 50 pounds, which means my mass is 50 over 32.2 to get a mass in slugs, times the initial velocity. Initial velocity was 3 feet per second, plus summation of my forces times time. So I have that P force is 20T. And since that force is variable with time, I'm going to have to keep it in integral mode, which is going to be integral from 0 to 2 seconds of 20T dt minus the force from my friction, right? I've got friction force in this direction. My friction force is 0.3 times the normal force, which I didn't find. I'm going to need to find my normal force, times the time interval of 2, plus my weight has an x component as well. At this angle of 30 degrees from the normal. My weight has a component as well. Since it's a constant force, I can just do the force times time. So that's going to be my 50 pounds, and then the portion of that that is in the x direction is sine 30 times the time of 2 seconds equals my mass, which is 50 over 32.2 times V2. Whew, that was a lot, right? But I have almost everything I need. The only thing I don't have is my normal force. But I know since there's no movement in that y direction, I can find that normal force just from my statics. So from statics, if I do summation of y forces, and again, you could use the y summation of your impulses as well if you wanted to. You could use work energy, or not work energy, you could use F equals ma. Of course, that's going to equal 0. But from statics, if I do this summation, I'm going to get my normal force minus the y component of the weight, which is 50 cosine 30 equals 0. So my normal force equals 43.3 pounds. And I can plug that in for my n, and I can integrate that t. So that's going to give me, I continue this on down here, this first term from the calculator is 4.66, plus the integral of this guy is 20t squared over 2, evaluated from 0 to 2, minus 0.3 times the normal force of 43.3 pounds times the time interval 2, plus 50 sine 30 times 2 just gives me 50, equals 50 over 32.2 for the mass times V2. So when I simplify all of this, I'm going to get 4.66 plus 40 minus 25.98 plus 50 all over, this guy simplifies to 1.55, so 1.55 is V2. So for V2, you should get around 44.2 feet per second, which is fast. This thing is zooming. After only 2 seconds, this huge amount of force, combined with the fact that gravity is contributing, this thing is moving fast after 2 seconds. So that's our impulse and momentum. We'll be working a little bit more with impulse and momentum, conservation of momentum, more impact, these kinds of problems as we continue on. But this is our basic principle of impulse and momentum.